Analytical Chemistry 1, Lesson 11. Let's continue speaking about error propagation. This is the most generally employed expression for error propagation. Again, it hinges on small errors for uncorrelated variables, which is commonly the case. We also assume the errors are distributed normally. It's a Gaussian distribution. This is a common situation in much of experimental science. However, when conclusions derived from our experiments are crucial, for example, achieving regulatory compliance, or the outcome of a criminal trial, or ensuring public safety, you may need to delve deeper into the field of error propagation. But these simplified relations will work well for much of your career's needs. We do not usually use this expression directly in each case. Instead, we can solve these derivatives for various common functional relationships, which will provide us with a series of standard equations that we can use. It will be these relationships that you will need to recall during this course and during much of your career. Here are the common ones we need to remember. The first functional relationship we will consider is to just multiply a single variable by a constant. The derivative of ax is just a. The variance in f is then a squared times the variance in x. We now take the square root, and the standard deviation in f is just a times the standard deviation in x. Next, we consider the sum of two variables, a times x and b times y. The partial derivatives are just the coefficients a and b, so the variance in f is the sum of the variance in x and y scaled by the square of the multipliers. The square root of that sum of the variances is the standard deviation of f. If this is addition, then what about subtraction? Take the difference of two variables a and x and b times y. The partial derivatives are just the coefficients a and minus b. The variance is the sum of the scaled variances. The standard deviation is the square root of that same equation again. Note that addition and subtraction leads to the same error propagation equations. The absolute standard deviation of the sum, or the difference, is the square root of the sum of the squares of the absolute standard deviation of each variable. This you should remember. It is worth mentioning that if there was a correlation between x and y, then the covariant term would have a different sign in the two cases, so there would be a difference. But for our uncorrelated situation, they are the same. Okay, let's look now at multiplication and division. First, consider the function of the product between two variables, a times x times y. We will again assume some constant multiplier a just to make it generally applicable. The partial derivatives are ay and ax. The variance expression leads to something a little more complex. Here's some white space to work it out. In this case, we first get a squared y squared sigma x squared plus b squared x squared sigma y squared. Not sure what to do with the x and the y? Well, we sort this out by dividing both sides of the equation by f squared, the original function. We obtain this expression, and once we cancel the terms in the denominator and numerator, we obtain this relationship. Recall how the standard deviation of a variable divided by that variable was called the relative standard deviation. This relationship is the sum of the squares of the relative standard deviations. The relative standard deviation is the square root of the sum of the squares of the relative standard deviations, which are just the relative variances. Here we now have the division of one variable by another. The partial derivatives are a over y and a times x. We do the same thing as with multiplication. I am leaving it to you to work through, but you should find the division expression is the same as multiplication, the sum of the square of the relative standard deviations. We take the square root for the relative standard deviation of the function. This is to be remembered. For addition or subtraction, to find the absolute standard deviation of the function, take the square root of the sum of the squares of the absolute standard deviations. By contrast, for multiplication and division, to find the relative standard deviation, take the square root of the sum of the squares of the relative standard deviations of the variables. Recall that you can always turn a relative standard deviation into an absolute standard deviation by multiplying by the value of the function, which is your answer. These are the most important relations for the class, but I want to mention four more as you may find occasion to use them. The power function has x raised to the power b and multiplied by a. The derivative is a times b times x to the b minus 1. Substitute this into the expression. You'll want to divide by f squared again. Cancel things out. Can you see why x to the b minus 1 squared divided by x over b squared is equal to 1 over x squared. In the end, we find the following, and the square root of this gives us the relative standard deviation for the function. Now here's a thought experiment for you. We can think of the power function as just x multiplied by itself b times. Could we not just use the multiplication propagation formula? Work through it and you will get a different result. Why? The difference is that in x raised to the b, the individual x's are highly correlated with each other. They are all the same. The multiplication expression we are using is assuming independent uncorrelated variables, and thus the power equation gives a different result when applied correctly. For the last three, we will find an additional variation on this theme for logarithmic and exponential functions. First, the natural logarithm function. Constants a and b show up. The derivative of the ln function is just 1 over x. Use the chain rule to make sure you incorporate the constants correctly. Substitute in to find the variance of f, and the square root gives the standard deviation. Note what happens here. The relative standard deviation of the variable becomes the absolute standard deviation for the function, scaled by the a constant but not the b constant. The similar thing happens if you use base 10 logarithms. You just have to include the scaling factor of ln 10, which is about 2.303 to convert the natural logs to the base 10 logs. Again, the relative standard deviation becomes the absolute standard deviation. And finally, the exponential function. Recall that its derivative is itself, but get the constants right. Substitute it in. You'll again want to divide both sides by the original function, carefully cancel the constants, and obtain the final result that absolute standard deviation of the variable becomes the relative standard deviation of the function's result. Now, you might have expected this result when you adjust the converse for the logarithms. Look carefully to see which constants are the multipliers. They also play the essential role of getting the units right. To wrap up this era of propagation, let's return to our calculation of the molarity of the sodium nitrite solution. Here's the function that takes our measured inputs: atomic molar masses, mass of sodium nitrite, volume of the volumetric flask. You can apply the propagation equations in sequence. First, multiply the standard deviation for oxygen by 2. Then combine the absolute standard deviations for the three elements as the square root of the sum of the squares to get the standard deviation for the molar mass of sodium nitrite. Here now are the three variables along with their standard deviations, which we combine to find the concentration. You're just left with multiplication and division, which, within our framework, have the same relationship for error propagation. Divide each absolute standard deviation by the value of the corresponding variable to get the relative standard deviation. Now combine these as the square root of the sum of the square to get the relative standard deviation of the result. You can now multiply it by the final value of the function. Remember that we found that in the last lesson its value is 0.76735 molar to find the absolute standard deviation. We can report the concentration of the solution as 0.7674 plus or minus 0.0006 molar. One thing worth noting: if you look at the numbers, you will see that the final uncertainty is dominated by the uncertainty in the volume of the volumetric flask. Relative uncertainty in concentration is 8.01 times 10 to the minus 4, while that for the flask itself was 8.00 times 10 to the minus 4. The uncertainty in the weighing is small, and the uncertainty in the molar mass of the atoms, and hence in the molecule, is almost negligible by comparison. If you wanted a hand-waving estimate of the final uncertainty, you could have just taken the relative uncertainty of the volume. Our calculation is also an estimate because of the approximations taken in the development of the expression, but the hand-waving estimate would ultimately give almost the same result as our longer calculation. Over your career, you will develop an eye for the math, and you will start to see approximations quite quickly. But it is best to do your full analysis and compare it to a hand-waving estimate as a means of confirming your math to make sure you haven't made a mistake. Now, this tells you one more thing about your experimental design. If there is one thing you could do to improve the precision of your work, it would have to do with the measurement of the solution volume. One easy way to cut down your uncertainty by as much as an order of magnitude would be to weigh the solution with an analytical balance. This is another of the situations when molality is a better concentration measurement than molarity, but admittedly the error in molarity in this case is less than 0.08%. And that's not bad. It's very useful for many experimental procedures, and so we continue to use molarity. This is one way to report a measurement with statistical significance, the sample average plus or minus the sample standard deviation.